All right, let's start. So today is our second lecture of this term, and it's still about a lot of concepts and not the real techniques. But that's intentional because in the first week, like we are still getting students enrolled, and we are trying to set things up, and there could be some bugs or issues with the classrooms or all the systems. So that's why we just cover some concepts in the first week. So today we are going to learn about verification and validation techniques. And yesterday, this is today's outline. And actually yesterday we have learned that a desirable software is a dependable software. And there are 4 properties related to software dependability. So can you still remember them? Like what are the 4 properties? So do you still remember the figure? So the first one is reliability, and then we have correctness, and then we have safety, and then we have robust, right? So these are the 4 properties. And we know that, okay, we want dependable software, and testing can help us to get the dependable software. But there's still a gap to this question, because testing is not the only approach for us to build dependable software, for us to do quality assurance for software. There are many other techniques. So where is this software testing positioned in this big picture of the entire software quality assurance field? So this is what we would like to answer today. And the process of making software dependable is often known as verification and validation. And let's jump into the definition from the textbook. So these are the definitions for verification and validation. So for verification, it is the process of proving that software conforms to the specified functional and non-functional requirements. And for validation, it is a process of proving that the software meets the customer's true requirements, needs, and expectations. So these are kind of confusing and overwhelming, right? It looks very similar. It's like they are all related to proving something, but the thing we are trying to prove is like somehow different, right? So what's the difference here? So let's try to make it simpler. So this guy is the person who invented the term. He doesn't invent the whole field, but he's the inventor of the term, software engineering. So because in early days, when people do programming, they don't program software directly. They program somehow like programming hardware directly by plugging and unplugging the circuits. So he is the inventor of this software engineering term. And this guy, Barry, he describes verification and validation as, for verification, it is about, are we building the product right? And for validation, it is about, are we building the right product? So you can see that, for verification, we care more about the process of building this product, right? We care more about the intermediate steps achieved when we are building the product. And for validation, we care more about the final thing we get, right? So now let's jump into the details of verification and validation. So for verification, when we talk about verification, another keyword that is associated with this term is often known as specification. So we need to verify against some specifications. And normally we try to compare source code and the requirement specifications. And we try to compare, we can also compare detailed design and high-level architecture. Or we can try to compare the test oracles. This is a technical term that we will learn later, and the requirement specification, and so on. So verification is more like an experiment. And it is an experiment about, does the software work under certain conditions? And we can perform trials, we can evaluate, and we can provide evidence for the verification process. So it's all about this process. And for validation, it is somehow different. So we care more about how does the final product perform, especially in the real world, in the real world settings. It's not like an experiment which is conducted in a controlled environment, right? It's more about how does it perform when deployed. So it cares about, does the software fulfill the actual need of the users. It's not, and normally the actual requirements from the users may not be the same as the design specifications, right? Which was used for verification. So validation can help us to show that, okay, this software is useful, but it may not show us that it is correct against some specifications. So it only shows us that this software is useful. And verification shows that, okay, it's dependable, it's correct. And here is a comparison between these two techniques. And again, it's like a little bit overwhelming, but we don't need to care about all the details here. We care more about some key terms here. So for verification, so we have learned the difference between static analysis and dynamic analysis yesterday, right? So do you still remember what's the difference? Why a technique could be called dynamic? What makes it dynamic? The difference is that dynamic analysis techniques often requires us to run the software, right? To execute the software. And for static techniques, we don't need to run the software. We just put it there. We just scan through the software. It doesn't need to be executed. So normally, verification techniques are considered as static, but validation are considered as dynamic. That's because for verification, we are checking the implementation against some specifications. So we don't have to run the software to do this, right? To do this check. And for validation, it is different because we care more about the performance in real world, in the deployed environment, not in a controlled environment. So that's why we often need to run the software when we do validation. So that's why one is static, the other one is dynamic. And the second key thing here is that this was actually a screenshot from a textbook, and by that time, verification was normally done by human experts manually. So people are writing some mathematical proofs to prove that the software can really meet some specifications. So it is often like a human-based process. But nowadays we have a lot of software to assist this process. So it's not fully human-based. It's automatic or semi-automatic. And as you can see, testing is considered as a validation technique here. And both of them can catch the errors that the other one may not be able to catch. So these are the key points. And there are several limitations that limit the performance of these techniques. So the first one is the conflict between complexity and cost. So many techniques could be very complex, and they could cost us a lot when we try to apply them. Like the cost could be time cost, the cost could be human effort cost for using these tools. So this is one of the limitations. And the second limitation is we may not be able to achieve a very complete coverage to cover all the aspects of a software. So it's very normal that we cannot fully guarantee that software is a piece of software is dependable after the verification and validation process. For example, for all the commercial products we are using nowadays, even for those which are released by the large companies like Microsoft, they still have bugs, right? We may sometimes still encounter bugs. So it is often impossible to achieve a complete coverage of all aspects. And there are limitations for the tools we are using. So because verification and validation nowadays the software are very large, like there are millions of lines of code. So we cannot manually inspect all of them, right? We have to use some automatic tools. And these tools, each one of them have their own limitations. And we will learn about them later. And there are human factors because eventually it is the humans who are using the tools. And it is the humans who are designing the strategies of using these tools. So the human factor, if a person who is more experienced uses the tool, then the result could be better. But if the person is not very experienced, then the result could be bad. So these are the limitations of verification and validation. So now we know that, okay, so verification is more about the process, more about the intermediate product, and is often static. And validation is often more about the final product, whether it works in the after deployment, and it's more dynamic. So now let's learn some different types of actual techniques for verification and validation. So this is a taxonomy of different verification and validation techniques. So we can see that most of the verification techniques are considered static, and most of the validation techniques are considered as dynamic. And we will be learning black box or functional testing in week 2, and we will learn this in week 3 and week 4. And in week 2, this is also related to your assignment 1, and this is related to your assignment 2. And this used to be related to the assignment 2 in previous terms, but now we removed it. And we are not going to cover static methods in this course. After this class, we will briefly go through these static methods in this class. So for static methods, it is to scan through the system to look for patterns, suspicious patterns for bugs. So it is similar to how we scan a patient for some disease, right? So similarly, for a piece of software, for a piece of code, we can also try to look for some suspicious patterns. For example, if we are trying to access a buffer, there could be some patterns of checking whether this value, the index of the buffer is out of bound, right? So there are some significant or some useful patterns for looking for bugs. So for static analysis, we are often trying to scan the code, and scanning the code may require different techniques. For example, we can do formal verification, which requires the user to write formal proofs to prove that, okay, this piece of code satisfies certain property. And that property could be maybe, okay, the loop will loop 10 times or less than 10 times, things like that. Or maybe the buffer, because loop matters here because loop can affect the value of the indexes sometimes, right? So we can also prove that, okay, this buffer will never overflow, things like that. So it's called formal verification. And we can also do software composition analysis, which is related to checking the composition of the software, because modern software are often not written from line by line. We often use libraries, right? So if we do SCA, we can try to analyze which are the libraries we are using and what are the versions of these libraries. So we can know that, okay, if we are using an older version of the library, then there could be some bugs from that library, right? So this is also a way of finding bugs. And we can also do static tent analysis, which is to track whether the user input can reach certain location or not. So if the user's input can reach some part of the code, then we know that, okay, this piece of code is more interesting for us to check, right? So that's static analysis methods. And for dynamic methods, it's more about exercising and observing. So we run the code, we exercise the code, and then we observe whether the software behaves wrongly during the execution. So it is considering the hospital example, we are actually asking the patient to do something and then observe how does the patient perform when he or she is doing the task, right? So these are the advantages and of dynamic methods comparing to static methods. So sometimes some bugs can only be exposed, or some information can only be acquired when we run the software. For example, we can somehow estimate the memory cost of a piece of program, right? But we cannot know the exact memory cost, or maybe the peak memory cost of that software unless we run it and monitor it, right? So there are many information that we can only acquire when we run the software. So that's one of the most significant advantage of doing dynamic analysis. And there are some other advantages. For example, dynamic analysis techniques are often easier to be automated because those static analysis may often require humans to do some proving using some automated tools. So that's the advantage of dynamic methods. So do you know what are can you quickly come up with a limitation of dynamic method comparing to static ones? So what is the limitation? So we know that, okay, it has advantages. It's easier to be automated. It can get runtime information, but what's the limitation? So if it doesn't have this one is one of the limitations. So we cannot run the software forever to run all the possible situations, right? Sometimes there could be many different corner cases for us to run, but can you quickly come up with another example of the limitation of dynamic method? So the limitation lies in its name. So because it is dynamic, we need to run the software. And sometimes running a piece of software is not very easy because we need to set up the environment, right? It may have dependencies. It may have software dependencies. It may have hardware dependencies. So sometimes it could be hard for us to set up the environment for running the software. So that's another limitation. So now we have learned about different techniques, and let's have a quick live poll here. So which systems do you think are formally verified? Formal verification means that the human experts are trying to inspect the code and try to prove that the code satisfies certain properties. So all the systems here are tested. I can guarantee you that they are all tested but are they all formally verified or not? Okay, let's see the results. Seems to be pretty good. Actually, all of them are formally verified. So we know that they must have been tested. But formal verification, as I just mentioned, requires human experts to actually prove something right, requires a lot of human experts. And we know that nowadays, the key systems we are using right now are verified by some experts. So for example, some C compilers are formally verified, some OS kernels are formally verified, and some smart contracts are also good targets for formal verification because smart contracts are directly related to money, and often these contracts, the code for these contracts are not very large, so we can afford manual verification for these smart contracts. So, and there are some new startups which are doing this formal verification for smart contracts. So we know that, okay, so for key systems, we still need to formally verify them. For larger code bases, however, we cannot afford to hire all these experts to do verification, right? For some systems, we may have millions of lines of code. Then how can we like ask humans to do formal verification for them? So we have to have both verification techniques, and we also need to have validation techniques. And how do we however, how do we evaluate these techniques? How do we choose which technique to use under different scenarios? So it is actually a game of trade-offs. We need to consider, we need to balance the performance and the cost. So software engineering itself actually is a process of getting the best ever result from a limited set of resource. So like other software engineering problems, we often need to have the trade-off between what we want, what we need, and what we have, right? So we can, so like mentioned by a NASA engineer, it's like we can choose better, faster, or cheaper. We can choose any one of any two, but we cannot have all three of them. And we must accept some degree of inaccuracy with whatever technique we try to use. And this inaccuracy is related to the inaccuracy of identifying a bug. So where does these, so what are these inaccuracies? So there are actually three types of inaccuracies here. So the first one is pessimistic inaccuracy. So pessimistic inaccuracy means that we are trying to be pessimistic. We try to suspect that the software is not safe, is not dependable. So in that case, whatever looks suspicious, we mark it as a bug. So this is pessimistic inaccuracy. And what can you tell me what does pessimistic inaccuracy lead to? Does it lead to false positive or does it lead to false negatives when we find bugs? We mark anything suspicious as a bug. Is it false positive or false negative? It's actually false positive. So because it's related to reporting bugs. So positive means positive means we raise the flag that here's a bug. So that so it leads to false positives. And on the other hand, we have optimistic inaccuracy. Optimistic inaccuracy means that we have a set of hard requirements as far as this software can meet the hard requirements. We say that, okay, this software is okay, we can accept it. So in this case, we are missing some bugs, right? So we are suffering from false negatives. And another side of inaccuracy is from the property complexity. So in real world cases, the software could be very, very complex, and we may have to model the software into something simpler to verify the properties of the software. And this modeling process can lead to the miss of certain properties. And then we are missing some properties of the program. So we can have some inaccuracies here. But this is more related to formal verifications. And what do you think is the inaccuracy of testing according to the definition? Actually, I forgot to hide some information on this slide. You can find the answer from the slide, but can you try to answer without by just looking at the definitions? So pessimistic is about we report everything suspicious. Optimistic is that we have a set of requirements. As far as these requirements are met, we just say, okay, this software is okay, it's acceptable. So what kind of inaccuracy does testing have? It's actually optimistic inaccuracy, because according to the definition, optimistic inaccuracy is that as far as certain requirement could be met, right? And that requirement could be like passing all the tests, right? So we can say as far as we pass all the tests, we can accept the software. So testing is often leads to optimistic inaccuracy. And most of the time we are missing bugs rather than reporting wrong bugs. So that's testing. And talking about inaccuracies, there are actually two relevant technical terms related to this, which is often used in the field of program analysis. And these two terms are soundness and completeness. So soundness means if a technique identifies only true positives, then it is sound, which means that whatever is reported by this technique is truly a bug. Whatever is flagged is truly a bug. It has no false positives. And the technique is complete if it can identify all the potential bugs. So soundness is related to optimistic inaccuracy, right? And complete could be suffering from pessimistic inaccuracy, right? Because we want to report everything. So what do you think? Do you think testing is sound, or do you think it is complete? Or both? Actually, testing is, most of the time, it is sound but not complete. So, and the reason is that we cannot, in real programs, we cannot use testing to cover all the potential situations. So And you will learn that by doing the practices and learning the actual techniques. So we cannot exhaustively test a program, especially real world programs. And so it is not complete. But it is often sound because testing requires us to really execute the program with some input, right? If something went wrong, if something observed is wrong, then the system must have some errors, right? So testing is often sound. So we don't report false positives most of the time. And that's all about different types of verification and validation techniques. And now let's move on to verification and validation planning. So this is more related to the practical usage of different verification and validation techniques. So like we just mentioned, one of the limitations of these validation and verification technique is the human factor, right? So because humans are the ones who plan the strategies of doing this verification and validation process. So now let's talk about how should we plan this process. So normally we have 7 steps to do. And for this part of the slides or lecture, you don't need to remember all the 7 steps. You just need to appreciate, okay, here are the 7 steps and why do they make sense, okay? So now let's jump into step 1. So step 1 is to identify the goals for doing this verification and validation. So the goals of doing verification and validation could come from the software requirements or specifications. And this is more related to verification, right? Requirement and specification. And the goals could also be from user expectations. And these types of goals can often are often related to validations, right? Because validations care more about the final product we have. And these goals must be achievable to take into account of the resources we have, because we always need to have some kind of trade-offs like time, like human effort, right? And for these goals, we could also have some more detailed goals sometimes, because we may have a very large piece of software. We can also we may also need to decide which part of the software should we focus more, should we allocate more testing effort to, right? So that's the first step. And the second step is to select a suitable verification and validation technique. And this is a lot of different things. So you don't need to go through all these. And we just need to know that for all the phases during a software, for all the phases in a software development life cycle, we can do verification and validation. And in this course, we will cover the techniques that deals with the implementation and maintenance phase. We don't care about the techniques for the earlier phases of software development. And now let's come to the third step. So the third step is to clarify organizational responsibilities. So this is more about splitting the testing effort across different teams, because when we do real world software development, we may also we may, especially in large companies, we have different teams, and some companies, they even have dedicated testing and quality assurance team. So but testing and quality assurance is not only the tasks for that particular team. It is also a responsibility for the developers. It is also the responsibility for the contractors, for the third party people. So this is the third step, and the fourth step is, since now we have our goal, and we have suitable technique for the goal, and we know which team should do what, right? We have covered all these three topics. And now we have to actually use the selected technique into our development process. So this step is to integrate these V&V approaches into the process. So and this integration actually depends on which development style we have. For example, if we do waterfall development, what we often do is we delegate the testing tasks to a dedicated testing team, right, after the software has been developed. And if we do agile development, often the testing tasks are done by the developers themselves during the development process. So this is how we integrate. And the fifth step is we need to do proper problem tracking. So now we have integrated, in the first step, we have integrated the V&V techniques. So the V&V techniques will start to give us flags or bugs, right? So now what we need to do is we need to track all the problems or bugs we have identified. And this problem tracking often requires us to document the issues properly. And these are the typical information to be collected. And here is, and can you quickly think of a scenario or an example of problem tracking? So in real life, you have encountered. Do you guys use GitHub? Yes? Okay. Yes. Issue board is a good example here, is what I'm going to show you here. So do you know what is the most starred repository now on GitHub? Have you heard about the news? What is the most starred? Do you know the star feature of GitHub? You know the star feature of GitHub, right? If I click on some repository, I can star it. It's like I'm putting it into a collection, so I can revisit this repository later, or I can receive news or updates from this repository. So there's a star function here. So do you know what is the most starred repository now? What is the most starred repository? You must have heard about that software. And it was Linux. It was Linux. So it was the Linux source code. And I think this is just a mirror of the actual Git repo here. This is a mirror on GitHub, but it was the most starred project. And now it is open cloud. So it is open cloud. And you can see it has like 377K of stars, of followers, like, and there are 2,000 something branches. And you can see the issues are like thousands of issues or tens of thousands of issues. And I even opened the pull request and got closed, but because it was implemented somewhere else. So you can see that it's very hard to manage, to really track the problems, to really maintain this, especially during this coding agent era, because as you can see here, the commits is like crazy. It's like 57K commits since this year. It was released this year. And people are coding like a lot, and there are thousands of contributors, as you can see here, to this project. So how can we manage the reported issues? We need to have some templates and formats. So as you can see here, if we try to report a bug, there are some templates we need to follow. And these templates often need to contain the information here, like this. So we need to specify when does the problem occur. So this when here requires several things. So when means in which step when you are using the software does the bug happen, right? When also means like maybe during a specific time the vulnerability or the bug happens, right? So that's when. And where the problem occurs, it's better if we can point this error to some locations in the code, right? And it's better if we can report the state of the system before the occurrence of the bug, right? So that's why when you see if your Python script went wrong, you'll see some errors or maybe some JavaScript goes wrong. Let me see if this web page goes wrong or not. So you can see here. So normally all the web pages, even the commercial ones, they can have some errors. You can see, yeah, but they are not very big ones. So if we click on these, you can see that they are often trying to show the location of the code, right? They are trying to provide this location information. And if we catch some, and for some of the exceptions, we have the context, the stack trace, which stores the information of the state of the system before the occurrence of the bug. So this is the purpose of the stack trace here, is to store the state of the system. And of course, we need to have some kind of evidence. And in testing, it is the test case that can trigger the bug, right? And sometimes we may also need to have a priority for solving the problem. As you can see here in this example, it has so many issues. So we have to have some kind of labels like P0, P1, P2, P3. So we have to prioritize the fixing order for different types of problems. So this is the example of problem tracking in real world, and especially a very large project. And an advantage of testing is that we can easily get the evidence of the problem. Because we can just use the test case that can trigger the bug as the evidence, right? If we find a bug by manual inspection, then we have to write some paragraphs to describe the bug, to try to describe it clearly, to try to convince the developer, okay, there's a bug. But for testing, it's often very simple. We just need to show them the test case. And the sixth step is that now we have got problems and we are keeping track of the problems, but we also, in real world, we also need to track the testing activities. So we may need to track the number of test cases executed. We need to track the time used. We need to track the resources used and like problems found, these kind of things. So the most important reason for doing this tracking is not only to keep track of what we are doing, but also to ensure to have a better performance, to improve our testing effort. That's one reason, but a more important reason for us to do this often in real world is that we need to show the effort we have devoted to test to ensure the quality of the software, because testing doesn't always generate bugs, right? Doesn't always give us bugs. We may not, because it's not complete, we may miss bugs. So how can we prove that this software can be trusted if there's no bug reported? And when there's no bug reported, so we have to show that, okay, here's the effort we have devoted to testing this piece of software. And because we have devoted a huge effort, then this software is somehow trustworthy. So this is why we need to track the activities. It is an evidence to show the trustworthiness of the target software. And the last step is that we may need to do assessments of the V&V process. So we need to. It is also related to the previous step of tracking the testing activities. So we may need to organize the activities we have tracked in a way that some third-party people can appreciate and recognize, because most of the companies, they do testing not only to ensure that their product is free from bugs, to improve user experience, but they also need to comply to some policies. Like for some critical software, when the governments are trying to apply some limitations or rules to make sure that the software are fully tested, are well tested before they are released. So assessment is to prepare some kind of report of our V&V activities to show to some third-party people, to show to others. So this is a quick summary of the 7 steps. So we need to identify goals, and once we have the goals, according to different goals, we can try to select different techniques, right? And we just learned what are the differences and like the advantages and disadvantages of different V&V techniques, right, earlier in this lecture. And after we have selected the suitable technique, we need to distribute the tasks among different teams. And then after we have settled with all these 3, we need to actually use these approaches in the software development lifecycle, right? And then once we have deployed the V&V techniques in the development, issues starts to popping up, right? Then we will need to do problem tracking, and we also need to track our testing activities. And all the problem tracking and testing activity tracking are to be used for the final assessment, to create the final report, to show that, okay, this piece of software is trustworthy, is fully tested. So that's the summary. And that's the first half of today's lecture, and let's have a rest for about 10 minutes, and I'll see you at 3 after 4. Okay, let's start. So just now we have covered like what's the difference between verification and validation. We have covered like different types of techniques under each category and their advantages and disadvantages. And then we covered
there could be some bug bounties. And you can imagine Microsoft is paying $60K per applications.
Someone in the meeting.
For example, if we can, if you have played with the flight simulator or created.
What happened? I think someone in the Teams meeting has forgot to unmute. Okay, anyways, just let's continue. So we learned how do we do this planning to apply these techniques in practice. And now let's learn some more theoretical things like the principles of doing these analysis and testing. So there are 6 basic principles. And again, you don't have to remember or recite all the concepts here because these concepts are the design principles that were summarized during this long history of doing software testing and quality assurance. So you just need to appreciate, okay, why people come up with this principle, why people come up with that principle. And we will encounter the application of these principles when we learn different actual testing techniques. So these are the 6 basic principles. The first one is sensitivity. The second one is redundancy, and then restriction, partition, visibility, and observability, and lastly, we have feedback. Let's go through them one by one. So sensitivity means how, as indicated by the name, how sensitive we are towards errors or bugs that happens inside the software. Because some bugs are very obvious. If the program crashes, if we see a blue screen, then we can definitely tell that, okay, there's something error. If there's an alert pop up, right? We can say, okay, there's definitely some error. But some errors and faults are not obvious. So we have to be sensitive enough to capture them. So for example, the web page I just showed you, right there, you can see that, okay, nothing is wrong here. But if you open the developer console, you can observe some errors logged. But these errors are like, if we use human as an observer, then we are not sensitive enough to identify the error, right? But if we use some program as observer, then we are sensitive enough to capture these errors. And similarly, some faults and some errors are so hard that even some software cannot find these errors. For example, if we read one more byte in C, then let's click on this example here. So in this example here, we have a buffer with 8 bytes, and if we just read with index 8, which means because the index starts from 0, so we are reading the 9th byte of the buffer here. This is a C program. So do you think there will be errors when we run this program? Do you think we can observe errors? There will be reported errors here. Actually, no. We are reading an uninitialized piece of memory here. So, but there is an error. There's an off by 1 read. So we cannot capture this. However, for this example here, so let's try to write 10 bytes into this buffer, outside this buffer. And here, this is output from the previous one. So you can see that this time the error can be observed. So the question is, can we be sensitive enough to capture all the errors? So that's the issue here. So the sensitivity principle here is to make sure that the failure is observable every time we run the program. So to make sure that all the bugs and errors can eventually lead to some failures that are observable. And well, as for the solution for this example here is we can try to use some compiler sanitizers when we compile the C program. And the sanitizer we can use to capture this bug is called address sanitizer. And we will cover the details of address sanitizer in later lectures. But you just need to know that, okay, we must be sensitive enough to capture bugs. Errors does not always lead to failures or something observable. So that's why we need to be sensitive. So this is the first principle. The second principle is that sometimes we may need to have multiple different tests or multiple different testing mechanisms to test the same target, the same functionality sometimes. So this can help us to increase the likelihood of catching these errors. And one example is that we can use ensemble fuzzing, which is another technical term that we will learn later. So this technique actually, as indicated by the name, it combines different testing techniques together to test the target. And as for redundancy, let's look at a small example here. So let's assume that we have an online shopping cart, and before the user clicks the pay button, the shopping cart checks only the final, whether the total value of the items inside the shopping cart matches the total calculated price. So if we just check the final price, what could be wrong? What could be wrong? So there could be multiple items inside the cart, right? And maybe, just maybe, a discount or a discount voucher was used to one of the item, and this item accidentally has the same price to another item. Then there is something wrong inside this process, right? There's something wrong inside this process. So if we just test the final process, the final price, we cannot capture this error. But if we check the price of each item against its own price, then we can capture the bug of a wrongly used discount voucher. So the takeaway here is redundancy is not just about more tests. It's more about if we try to design tests from different angles, we can have more independent chances to notice the wrong behavior. So redundancy doesn't mean we repeat the test. It doesn't mean like we instead of just testing the final price against the total thing and repeat another, test it another time, write a different test that also tests the same thing. It doesn't. It's not like this. It's not as simple as writing more duplicate tests. It's more about how do we design orthogonal tests that can complement each other. So this is redundancy. And here, the third principle is restriction. So restriction is actually more related to analysis than software testing, but since it's in one of the 6 principles, we also introduce it here. So restriction means when there is sometimes a piece of program could be very hard to check or to inspect. So if there is no, because of the complexity of the code, the logic of the code, if there is no effective way to check certain properties, we can try to simplify the problem by modeling that piece of code into something simpler. So this is called restriction. And an example here is, this is actually a piece of Java code. So this integer k here, if we look at the program here, this integer k, there is a chance that the value of k is not initialized before it's used. Here we can see that k is used in this line here, right? K plus equal to I, which means that we add I to k. But k is initialized under this if branch. So what if this if branch is not satisfied, and then we directly goes to the else branch? Then it means that we are using k before it is initialized, right? There's this usage of uninitialized variable problem in this program. And it is actually very, very hard to automatically, determine whether this uninitialized usage could happen, because the condition function could be very complex, and maybe it could be impossible for us to check whether it could be very, very hard to check whether this I here can satisfy the condition here. So this is very hard to determine. So this is a hard problem to check. It's hard for us to determine whether k, there could be a, it's hard to confidently say that, okay, there could be an uninitialized usage of variable k. So what we do is we don't need to care. The end goal is to have a dependable software. So we don't need to care whether this may happen or not. We just don't allow it to happen at all. So the simpler or more restrictive property we want to have here is we just don't allow all the paths that can potentially have uninitialized variables. So this is like pessimistic inaccuracy. So we just don't allow them to happen. So this is a simplification for this, a simplified solution for this problem. So instead of trying to guess, okay, whether this k can be used before initialization, we just don't allow it to happen. We just say that, okay, this is dangerous. This is not allowed. So we just report an issue here. So that is restriction. So instead of trying to get an accurate solution, we try to restrict the property and try to work on a simpler problem. And actually, this restriction guides the design of the Rust compiler. So if you want to write safe Rust, sometimes it doesn't allow you to do something, right? So it's actually over restriction, and it's pessimistic. It's more pessimistic about the program. But this restriction here, as you can see, is more related to software verification rather than validation, because we need to model the program. We need to inspect what's happening inside the program. And the next principle is called partition. So partition, it means divide and conquer. So there are many different ways of doing partition. and we can do partition according to the different levels of the program, because programs can be very, very large, like millions of lines of code, and we cannot test the entire program all at once, right? We must be able to, we must be testing them part by part. And how do we do this partition is the problem here. And that's about the target itself. And because testing requires us to create test cases, right? And a program can often accept all kinds of inputs. Like, for example, if you have a text field, you can key in all kinds of strings, and the string could be sometimes infinitely long. So there are many different. The input space is also infinite. So we also need to partition the input space sometimes. And let's see an example here. So, for example, we want to test the login flow. And sometimes the login flow may require you to have usernames, may require you to have passwords, may require you to have two-factor authentication code, and also the account state. So if the account is disabled, then we cannot log in, right? So there are, as you can imagine, there are many different combinations between usernames, passwords, and two-factor authentication code, right? Maybe there are some mismatched username and password. Maybe the username doesn't exist at all. Maybe the password is wrong. Maybe the account state is like the account has been disabled. So there could be so many combinations, but the bugs can only occur under some very specific situations. So we are like finding a needle in a haystack, right? We try to find from all the different combinations a particular pattern to trigger the bug. So instead of trying to exhaustively try out all the combinations, what we can do is we can split the input space into meaningful parts. For example, these are the actual techniques that can be used to split the input space, but we will be learning the details in the next week. What we can do is, since maybe there's a bug appears with a locked account and valid password and expired two-factor authentication code, then instead of trying to try out all the combinations of username passwords, what we can do is we can try to partition the input space. We can try to group the inputs together. Maybe the username can be either valid or invalid. Password can be whether valid or matching or not match the username, right? And two-factor authentication code could be expired or not expired. And account state could be locked or not locked. So in this case, each one of them has two choices, and the total search space could be limited down to 2 to the power of 4, which is 16. So instead of typing all the combinations, we can just group them together, and by putting labels to these variables. And in this sense, we are like kind of like picking the representative values as our test cases, and then try to lead these combinations towards the risky area. So that's the principle of partition. And you don't need to remember all the details, all the terms here. You will appreciate why it works once we learn these actual like equivalence class or boundary values testings. Yeah. So you just need to know that, okay, because the input space is infinite, we have to do partitioning. Because the software is so large, we have to do partitioning to test the software part by part. And next principle is visibility and observability. So visibility is to make sure that the progress can be seen. So we know that, okay, this, so we need to have clear knowledge about where is our current state of development or testing. So for example, if we are during the development, we care more about unit testing. If we have developed the software, we need to do system testing. So visibility is to make sure that we are to make sure that we know the progress. And observability is to extract useful, to make sure that the problems or the issues are really tractable. So we just mentioned about tracking all the problems during the soft V&V planning, right? So we need to make sure that the artifacts generated during this process could generate or emit some useful information for us to eventually debug the program. And here's another example. So let's say that we try to test a web service, and this web service just returned 500 internal server error. And you may have encountered this when you do 1531, but yeah. So when you see this, and if there's no request ID, there's no relevant log, and there's no saved input that can trigger this web service, then what would happen? So what will happen is that the team cannot reproduce or explain the failure, right? So with just the error message here without any other supporting information, we don't know what's happening. So what we will need to do is we need to expose useful evidence during the execution. We need to add logs, we need to have trace IDs, we need to have counters, we need to have assertions, we need to have readable outputs. And we also need to keep a record of the input of the test case that we used for triggering the failure. So that's what we do if we follow this principle. And the takeaway here is that you cannot fix a bug if you cannot observe it. And we need to provide evidence for testing, not just to have a list of pass and fails, right? That's only some statistics, but the final thing we want to have is the evidence of failures. And this also aligns with the problem tracking step of the V&V planning, right? And the last principle here is feedback. So we must be able to apply lessons from experience in process and techniques. So during the development of a piece of software, we may have fixed some bugs, right? Like for example, for the open cloud example, you can see that it has 57K commits, and many of them are related to bug fixings. And what was kept along this way is a set of test cases that can trigger those bugs, right? They were also included into that repository. So why are they doing this? They are actually following this feedback principle. So we are not only pushing forward the development process, but we are also collecting feedbacks and try to adopt the feedback into our code base. So this is the meaning of feedback. And this feedback can also help us to guide, to prioritize our test effort, of course. And because if a particular part of the code has some error before, like during the development, then when we design new test cases, we may need to prioritize that part of the program, right? So that's one kind of feedback we can have. And another feedback is if a piece of code is very complex, then it is somehow more likely to be buggy, right? Then we can also try to prioritize our feedback, our testing effort there. And we will learn more about different metrics for evaluating software complexity in week 4. And here's an example. So, for example, if a release failed because an invalid config passed the review, which means that there was a bug in one of the release in the history of the software, and the same style of mistake had happened before. So what can the development team do? What can this development team do? What they can do is they can add a checklist item. They can add a config lint rule, or maybe a new test. And this test is called regression test. And as you can see from the real world example, here is, you can see that this is not generated by me. This is generated with Cloud Code following their templates. So they have summarized this type of checklist. So this checklist is actually, you can see it goes through the type check, it goes through the linting, it goes through the different items here. And these items are actually summarized based on their previous bugs. So this is what the team can do in this case. So this principle helps, as we can see, obviously. So it can turn the past failures into our future protection. So whatever has failed in the past can be converted into some tests to make sure that the performance of the system doesn't regress, right? And often we are using fault taxonomies. We often use like a revealed checklist when we submit new code, like submitting a new pull request, and we also end up in a regression test suite, and this can also help us to prioritize our testing effort to test the more the more buggy area, right? And the takeaway here is the feedback can help us to make the V&V progress to improve over time, over the period of development, because we are enriching our testing suite with the feedback. And the process should also try to learn from all the bugs we have encountered. So this is the principle of feedback. And here is a comprehensive comparison of all the principles. So for sensitivity, so so you will encounter them in future lectures. So for sensitivity, you will learn these address sanitizer. Briefly, the mechanism of address sanitizer. You will learn about the boundary value test cases. And for redundancy, it's automatic. Because we will be learning different techniques. So you can try to apply different techniques once you are really developing your own software. And for restriction, it is more related to verification. However, there's one concept that is kind of related to restriction, and that is test oracle. And we will learn about this concept later. And for partition, we will learn it next week. So for partition, we will learn how can we partition the input space. We will learn how can we do partitioning for the programs. So it actually guides us to work about how do we do black box testing and how do we determine different levels of testing. And for visibility and observability, they will also be related to test oracles and also white box coverage. If we have the source code, how can we count our test coverage to get more, to observe for more information? And for feedback, it's related to regression testing and software complexity. So all the principles here, they are not like coming out of nowhere. They are not like just coming out from the textbook, and we are not going to use it after we learn it. They are actually, they will be with us here, like for this course. And the final synthesis of this V&V process we have learned today is that it can actually provide us an evidence loop. So the first one is about the goal. So the goal is often related to what kind of properties matters here, like what do we care about when we do V&V, right? If we care more about the specifications, then we are more towards verification. If we care more about the actual user experience, then we are doing more validation. And then according to the goal, we are trying to select the technique, and the technique determines what kind of evidence can we collect to show that there is a defect, there is a bug inside the software. So for verification, we often show a description, or we often show the existence of the bug via some kind of description. And for validation or testing technique, we can show the evidence as a test case. And then once we have the technique, we can get the result, and the result is according to what can we observe, right? What can we observe depends on two things. Depends on how sensitive we are, and it also depends on the observability of the artifacts emitted during testing, right? And then after we get the results, we can make our decision. And after we made our decision, we can collect some feedback. So here, as you can see, these 6 principles actually helps us to build this evidence loop. So sensitivity and observability can help us to improve the evidence we have, right? Because if we are more sensitive, we can collect more evidence for proving the existence of bugs. If we have better observability, the information is richer, and it can help us to fix the errors easier later on. And partition and restriction can help us to make the problem more solvable. For example, because we have infinite input space, we can partition them by labeling them or grouping them together and select representative test cases. And because the software is so large, so we can apply different levels of testing by partitioning. And because the software is so complex, so we can apply some kind of restriction techniques to model the software as something simpler. So partitioning and restriction help us to make the problem solvable. And redundancy helps us to cover more, to reduce the number of blind spots, right? Because redundancy doesn't mean we are duplicating the effort. We are not duplicating any of the tests. Redundancy means that we are trying to approach the problem from different angles, from using orthogonal techniques or mechanisms. So redundancy can help us to reduce blind spots, and feedback makes the whole process learn by improving itself, right? Because we are collecting feedback, we are adopting things, we are enriching our test suite as we are finding more bugs. So to conclude, validation and verification is not a certificate. It's not to put a label to the software to say that, okay, this piece of software is trustworthy. It is actually a disciplined way to build confidence when exhaustive proof is impossible. Because when we have limited resources, when we cannot cover all the cases, we have to use some scientific and systematic way to show the others that this piece of software is trustworthy. It has gone through this V&V process, and this V&V process follows all the principles, follows all the plans, so that it is trustworthy. So that's all about V&V today. And let's have a quick recap of what we have learned, and then we will end the lecture. So what we have learned today is, first, verification and validation. So are we building the right product? Is this verification or is this validation? Are we building the right product? Is it validation or verification? Are we building the right product? Yes, validation. And I'm trying to ask this because you know the curve of memory, right? The curve of memory. No, not the pillow, but forgetting curve. Yeah. So if you try to remember things in like maybe 1 or 2 hours, if you recall what you have learned, then it's better to boost your memory. So it's kind of like this. So in the first day or after the first hour, you can memorize it better. So let's do a quick revision of what we have learned. So yes, are we building the right product relates to validation, and are we building the product right relates to verification, because validation cares more about the the performance after deployment, right? The performance from the user's aspect, and verification cares more about checking the alignment between the implementation and the specification or requirement. So that's the difference. And verification. And do you think testing is validation or verification? Is it validation or verification? Testing, is it validation or verification? Yes, yes. I think some of you has got the answer, but you are just too shy to to speak out. But yeah, it's validation. And so because testing is validation, so normally validation is considered to be dynamic, and verification is often considered to be static. And the advantage of a dynamic approach is that we can automatically get some evidence, right? Because the test cases can serve as the evidence or the proof of the existence of the bug. And then let's talk about soundness and completeness. So do you think testing is sound, or do you think it is complete, or both? It is sound, but not complete. We cannot use testing to cover all the potential scenarios. But whatever we report, if we report there's an error, then that error must be an error, right? Because we have run the program with the test case. If something went wrong during the run, then there must be an error. So testing is testing is sound but not complete. And let's move on to the next step. So it's about planning. So how many steps are there? So there are 7 steps. 7 steps, and let me think of a suitable question for you to ask, because that is not for you to recite, and you just need to remember that during this planning process, we need to keep track of all the problems. We need to keep track of all the testing activities. And the purpose of keeping track of these testing and problems is not only to improve the quality of the software, but also for the final step of assessment. Because we need to show, sometimes we need to show a third party that the software is trustworthy, especially for some software that requires policy compliance. So we need to have this assessment. We need to show that, okay, because this software has went through a systematic V&V process, so this software is trustworthy. So that's the purpose of V&V planning. And lastly, we covered the 6 principles. And for these principles, you don't need to remember all of them. You just need to know that we will be encountering them again when we are learning the different techniques. And the next technique we are going to learn are black box testing techniques. So that's all for today. And thank you for coming. Thank you.